All right, so for lab 10, we are looking at molar relationships. So we're going to be using molar masses to convert between grams and moles, which we've done a lot in chapter 4, and we're also going to be using mole ratios. So to use a mole ratio, we saw this in chapter 4 as well, what we need is a balanced chemical reaction. Okay, so we're going to have to go through all the steps, predicting the products, balancing the reaction, and then figuring out the mole ratio from there. So very similar to what we did in lab 9. Okay, so that's the first part. The new concept of this lab, however, is the fact that we're looking at redox reactions. So what redox reactions are, they're often called oxidation reduction reactions. And we know what an oxidation number is. We talked about oxidation numbers in chapter 3. So in chapter 3, when I brought up the concept of oxidation numbers, I said, don't worry, you already know what they are. We just haven't called them oxidation numbers yet, because what we've been referring to them as is the atom's charge. So all the oxidation number is the atom's charge. Is it a +1? Is it a +2? Is it a -1? Is it 0? Is it neutral? Okay, so what we're going to see in these redox reactions are that these oxidation numbers, the charges of the atoms, they're going to change. So magnesium, whatever the charge is of magnesium over on the reactant side, it might change over on the product side. So that's what we're going to look at, how these oxidation numbers are changing between the two sides of the chemical equation. And I do want to point out that redox reactions, so let me put a little star somewhere, there's no room, are usually single replacement. So what that means is single replacement reactions, remember to identify a single replacement, it's always an element by itself reacting with a compound and taking the place of one of those elements so that that element, in this case magnesium, is in a compound on the product side of the equation. All right, so let's start off this reaction by predicting the products. Okay, and if you remember, to predict the products, the first thing we want to do is figure out what these charges would be if these elements or compounds were in an ionic compound. I want to point out here, so magnesium is the element by itself. Anytime you have an element by itself, its original charge is 0. Okay? Let's look at hydrogen and chlorine. So what is hydrogen's charge? It's not by itself, it's in a compound, so it's going to have either a positive or a negative charge. And if you look at the periodic table, hydrogen's in that first column with the alkali metals. So hydrogen is a +1. Chlorine is a halogen, so it is a -1. So this is what their charges are currently, okay? But we know that magnesium is going to be in a compound on the product side. So when you look at magnesium on the periodic table, when it's in a compound, what is its charge? So I'm going to write that over here. So magnesium over here, it's going to be with a compound. And the charge on magnesium, when it's not by itself, is a +2 because it's an alkaline earth metal in period 2. So if magnesium's a +2 when it's in a compound, does that mean on the product side, is it going to be with hydrogen, who also has a plus charge, or is it going to be with chlorine, who has a minus charge? Okay, it's actually going to be with chlorine because we want a negative and a positive together. All right, so this will be one of our products, and we're going to figure out what the subscripts look like. But the other product then, the only element left is going to be hydrogen. And remember, hydrogen was one of those diatomic molecules, so it's going to be H2. Now what is magnesium chloride going to look like? To figure that out, we do that crisscross method, right? The 2 becomes the subscript on chlorine, the 1 will become the subscript on magnesium. So what I'm going to get, and write it up here, is Mg1 and then Cl2. Write it a little clearer. Mg, the 1, and then Cl2. So this is, let me erase this. Our product. The other product we said is H2, so what I'm going to do is just move that up here so it's all kind of in the same line, giving me some room here. And then to balance this guy, all we need is a 2 here. You can write down the list, do the atom count, and prove that to yourself as well. All right, so we have our balanced chemical equation. Now to figure out, in this oxidation reaction, who is oxidized and who is reduced, because that's one of the things you're going to have to figure out is which element was oxidized, which element was reduced. And to figure that out, all you need to know are those oxidation numbers, the atom's charge of each of the elements present. So we said magnesium, when it's by itself, has a charge of 0. It's neutral. Hydrogen, on the reactant side, since it's in a compound, its charge is +1. Chlorine, since it's in a compound, its charge is -1. And those numbers were found based off of where those elements are on the periodic table. Now over here, when we figured out what this product should be or look like, what the subscript should be, we decided that magnesium's a +2. So on the periodic table, it's an alkaline earth metal. Chlorine is still a -1. But what is hydrogen now? Hydrogen's now by itself, so is it going to have a positive charge if it's an element by itself? It won't have a positive charge anymore. So all elements by themselves meaning not an anionic compound, their oxidation number is 0, meaning their charge is 0. So since magnesium's by itself on the reactant side, its charge is 0 on the reactant side. Hydrogen by itself on the product side, its charge is then going to be 0. So we're going to use these charges that we have now written down to figure out which element has been oxidized and which element has been reduced. So to figure that out, we're going to use these tools that I have written here. Okay, so first I have a number line with oxidation numbers, okay, ranging from a +3 down to a -3, because that's to the typical range that we've been looking at in this course. So what this is showing, it's showing that if the oxidation number, when it changes, if it goes up in the upward direction, so from a negative to a positive or from a negative to a 0, that is the element that's been oxidized. If it goes in the other direction, down for instance, then that is the element that's reduced. There are also 2 monikers that you can memorize that help remember. So one of them is Leo the tiger says grr. So lose electrons oxidized. So if you're losing electrons, you're losing a negative charge, which means you're going to have a positive. Okay, if you lose electrons, that element will become positively charged. So that's the element's oxidized because it's going in that upward direction. So Leo, the line says grr, the grr part being if you gain electrons, it is reduced. So if you gain electrons, if an element or atom gains electrons, it's going to now have a negative charge. So it's going in the downward direction of this number line. Okay, so it's gaining electrons, it's going to be reduced. The other way to remember it is oxidation is losing electrons and reduction is gaining. So this is oil rig. So that's one of the ways to remember it as well. So once again, oxidation is losing electrons. And when you lose electrons, you're losing negative charges, so you're going in the upward direction towards the positives, because you're losing those negatively charged electrons. Reduction is gaining, so if you're gaining negatively charged electrons, you're going in the downward direction towards those negative charges. All right, so let's look at this balanced chemical equation and figure out which element is being reduced and which one's being oxidized. Whenever you have redox reactions, they always happen in pairs. That means you will have one element that's oxidized and one that's reduced. All right, so how to figure this out? I'm going to just pick this apart and figure out what's happening to every element present. So I'm going to start with magnesium. So magnesium is starting on the reactant side neutral, 0 charge. I'm going to draw an arrow, and then I'm going to write what happened to it on the product side. So on the product side, what is its charge? It's a +2. Okay, so did the charge on magnesium change? It did. It went from a 0 to a +2. So that means it was either oxidized or reduced. Okay, but which one? All right, it went from a 0. So I'm going to go over to my number line. I'm at 0. And it went up to a +2. So if it went in the upward direction, does that mean it was reduced or oxidized? It was oxidized. So what oxidation means is that magnesium is losing electrons. And that makes sense because you have to lose 2 electrons to get a +2 charge. Another way of looking at it, so how these are usually written, is you would put the +2 electrons over here. That's like saying plus a -2. So you can see that here, because electrons are negatively charged, so that's why I'm saying it's like saying plus a -2. Because that way, if you add those together, they should equal the charge over here. So a +2 and a -2 from those 2 electrons is going to equal that 0 charge. So since this magnesium lost 2 electrons going from reactants to products, it was oxidized. Went from a 0 to a +2. All right, let's look at hydrogen next. So hydrogen on the reactant side, right here, does have a charge because it's not by itself. It's in an ionic compound, so it has a charge of a +1. Now going over to the reactant side, what is its charge now? It's 0. Okay, because it is now an element by itself, and all elements by itself have a 0 charge. So what's happening to hydrogen? So to figure that out, I look. What charge was it on the reactant side? It's a +1. So I'm going to start at a +1 on my number line. And it's now going to a 0. So what direction does it have to go 0? Up or down? On the number line, it's going to have to go down. So it is reduced. And that makes sense because I said these happen in reaction-reaction pairs. So oxidized, one's oxidized and the other is reduced. So what reduction means is you're gaining electrons. So gain electrons reduced. Reduction is gaining. So that means this hydrogen is going to be gaining 2 electrons. And why did I say 2? Because there are 2 hydrogens present in this reaction, right? 2 hydrogens from the HCl portion, and then over here on the product side, 2 hydrogens because that's a diatomic molecule. So each hydrogen atom is gaining 1 electron for a total of 2 since there are 2 hydrogen atoms present. Okay, so what's happening here is this magnesium is losing 2 electrons because it's oxidized, and it's giving those 2 electrons to the hydrogen. So nothing is created or destroyed. They're just taking from one and giving to another. Now before we're done with this example, let's look at chlorine because there's still one element present. Okay, so we have chlorine on the reactant side and it's a -1. Going to chlorine on the product side, what's happening to chlorine? Still a -1. So notice, since it did not move on the number line, chlorine was not reduced or oxidized. It just stayed the same, because for it to be reduced or oxidized, its oxidation number, its charge, needs to change, and it didn't. So there's always going to be, in these examples in class, one that's oxidized, one that's reduced, and one that stays the same. So now let's apply this to the lab that we're doing for lab 10. So in lab 10, we are taking copper sulfate. We are then going to add iron powder to it. So if you watch the video of Dr. Rennie doing the actual experiment, you'll notice that when he took that blue solid that he weighed out, that copper sulfate, he dissolved it in water. So that's why I'm writing an AQ here, because since it dissolved in water, it's an aqueous solution. He then added Fe, iron powder, and the iron powder that he added was in solid form. So what we need to figure out is what the products are. We need to balance the reaction, and then we need to go through this process of who was oxidized, who was reduced. So to figure that out, first thing we want to do, since it's a single replacement reaction, right, element by itself reacting with a compound, let's write the charges as they are present here, and then the products over here. So copper, what is the charge on copper? That's the question, right? I don't know, because it's a transition metal. So to figure out the charge on copper, I'm going to look at its partner, and its partner is SO4, sulfate. So what is the charge on SO4, that polyatomic? Look at the polyatomic table, it's a -2. Okay, so how many sulfates are there? It's just one sulfate. So that means if this anion side is -2, what does copper have to be to cancel that out to make that compound neutral? It's going to have to be a +2. All right, let's go. This spot on here that won't come off. Over to iron now. What's the charge on iron? It is neutral because it's an atom by itself. It's an element by itself, so its charge is 0 on the reactant side. Okay, but since iron's a metal, when it comes over here onto the product side, it's going to take the place of the other metal. So iron's a metal, it's going to take the place of copper, since copper's the metal. So what we're going to see over here on the product side is iron mixing with the sulfate, SO4. Okay, and if you'll notice on your pre-lab, it actually has you calculate the molar mass of this compound. So this is actually one of the products. So you don't know the charge on iron. I'm telling you that the charge on iron, it's a +2 because the sulfate's a -2. Okay. So then that's going to leave copper all by his lonesome, making his charge what? Element by itself, it's going to be 0. This is +2, -2. Now these charges, we don't usually write them on a balanced chemical equation. I'm writing them so that we can figure out who's oxidized and who's reduced. Okay, so this is only to help me figure out which element's oxidized and which element's reduced. Should not be present in a general balanced chemical equation. All right, so looking at the products again, if you watch the video of Dr. Rennie, you'll notice that he weighed out at the end solid copper. So that was this solid right here, copper by itself. And that in solution now was iron sulfate. So that's why I'm writing an AQ by it. All right, so let's figure out who was oxidized and who was reduced. So to figure that out, I'm just going to pick an element. I'm going to write what's happening to that element from the reactant to the product side, use my number line and my knowledge here. So start with copper. So what is copper on the reactant side? Oh, my marker's running up. It is a +2. Okay, because it's in a compound on the reactant side. So on the product side now, copper is by itself, excuse me, so it's neutral, 0 charge. So what's happening to copper? Let me go over here. Copper is going from a +2 downward to a 0. So it is being reduced because it's going in the downward direction. And it's being reduced means it's gaining electrons to get reduced. How many electrons is it gaining? So if I gain just 1 electron, will that get me to 0? No, just 1 electron is going to get me to a -1. So it's gaining 2 electrons to go from copper +2 to copper 0. Because remember, electrons are negatively charged, so that's the same as adding a -2 here. Okay, +2, -2 equals 0. All right, so if copper is reduced, what do you think is happening to iron? Since they happen in action-reaction pairs, you can guess that iron's going to be the one that is oxidized, but let's write it out and make sure. Iron's going from a 0 to a +2. 0, so it's moving on up. So it's going upward direction towards the positives. It is oxidized. Okay? So that means that iron lost 2 electrons. Right? So just to make sure, let's check our last element or compound. In this case, it's a polyatomic. So we have SO4 on the reactant side having a -2 charge. On the product side, SO4 still has a -2 charge. So nothing happened to it. It wasn't reduced, it wasn't oxidized. Okay. Now, before we complete this lab, so we have to be able to predict the products, balance the equation, predict who's reduced and who's oxidized, but we're also going to need to figure out who is the reducing agent and who is the oxidizing agent. Okay, so this is actually, if you can figure out who's reduced and oxidized, it's just the opposite. So the reducing agent is the element or atom that's oxidized because it's reducing the other compound. It's the agent reducing the other one. The oxidizing agent is the element or compound that's been reduced. So This is why it's the opposite. The one that's reduced is the oxidizing agent. The one that's been oxidized is the reducing agent. So copper in this case, it has been reduced, so it is the oxidizing agent. And since iron has been oxidized, that means it is reducing copper, so it is the reducing agent. So this is just a definition, not really anything else to figure out other than to apply the definition here. All right. Well, let me know if you have any other questions on the lab. If you give me enough notice, I can do a video or try to set up a Zoom meet whenever we can figure out a schedule that'll work for us.